Hello guys, welcome to part 2 of this installment. Eventually, a Type 2 civilization may exhaust the power of not just its home star but all the nearby stars and gradually start the journey to become a Type 3 civilization, which is galactic. Not only can a Type 3 civilization harvest the energy from billions of stars, it can also harness the energy of black holes like the supermassive one located at the center of the Milky Way galaxy, which weighs as much as 2 million suns. If a starship travels in the direction of our galactic nuclei, we will find a vast collection of dense stars and dust clouds. That will be an ideal source of energy for a Type 3 civilization. To communicate across the galaxy, such an advanced civilization may use gravity waves, which were first predicted by Einstein in 1916 but finally detected by physicists in 2016. Unlike laser beams, which might be absorbed, scattered and diffused as they travel, gravity waves will be able to spread across the stars and galaxy and therefore may be more reliable over great distances. It is unclear at this point whether faster than light travel is feasible, so we need to consider for the moment the possibility that it is not. If only sublight travel are possible, then a Type 3 civilization may decide to explore the billions of worlds in their galactic backyard by sending self-replicating probes that travel at sublight speeds to the stars. The idea is to place these robotics on a distant moon. Moons make an ideal choice because their environments are more stable without erosion and they are easy to land on and live from because of their low gravity. With solar collectors to supply energy, a lunar probe can scan the solar system and radio back useful information indefinitely. Once it has landed, the probe will create a factory from the lunar material in order to manufacture 1,000 copies of itself, each clone in the second generation, then blast off to colonize other distant moons. So starting with one robot, we then have 1,000. If each of them creates another 1,000 robots, then we have 1,000,000 and 1,000,000,000 and 1,000,000,000,000. In just a few generations, we can have an expanding sphere containing quadrillions of these devices, which scientists call von Neumann machines. This in fact is the plot of the movie 2001, which even today portrays perhaps the most realistic encounter with an alien intelligence. In that movie, aliens put a von Neumann machine, the monolith, on the moon, which sends signals to a relay station based on Jupiter in order to monitor and even influence the evolution of humanity. So our first encounter may not be with a Buckeye monster but with a small self-replicating probe. This could be quite small, miniaturized by nanotechnology, perhaps so small that you will not even notice it. Conceivably in your backyard or on the moon, there is evidence of a past visitation that is nearly invisible. In fact, Professor Paul Davies has made a proposal. He wrote an article advocating going back to the moon in order to search for anomalous energy signatures or radio transmissions. If a von Neumann probe landed on the moon millions of years ago, it would likely use sunlight for its power, so it could continually broadcast radio emissions. And since the moon has no erosion, chances are it will be in near perfect condition and still in operation. Since there is renewed interest in going back to the moon and then on Mars, this will give scientists an excellent opportunity to see if any evidence exists for the presence of previous visitors. So even if light speed cannot be broken, a Type 3 civilization could have trillions upon trillions of probes spread across the entire galaxy within a few 100,000 years, all sending back useful information. Von Neumann machines may be the most efficient way for a Type 3 civilization to obtain information concerning the state of the galaxy, but there is yet another way to explore the galaxy more directly, and this is through something that I call laser porting. One of the dreams of science fiction writers is to be able to explore the universe as pure energy beings. Perhaps one day far in the future we might be able to shed our material existence and roam the cosmos reading on a beam of light. We will be able to travel to distant stars at the fastest possible velocity. When we are free of material constraints, we will be able to ride alongside comets, skim the surface of erupting volcanoes, fly past the rings of Saturn, and visit destinations on the other side of the galaxy. Instead of being a flight of fantasy, this dream may actually be rooted in solid science. Project this ambitious effort to map the entire brain. Perhaps later in the century or early in the next, we will have the complete map of the brain, which in principle will contain all our memories, sensations, feelings, and our personalities. Then the connectome might be placed on a laser beam and sent into outer space. All the information necessary to create a digital copy of your mind can travel across the heavens. In 1 second, your connectome could be sent to the moon. Within minutes, it could reach Mars. Within hours, it could reach the gas giants. And within 4 years, you could visit Proxima Centauri. Within 100,000 years, you could reach the ends of the Milky Way. Once it arrives on a distant planet, the information on the laser beam will be downloaded into a mainframe computer. Then your connectome could control a robotic avatar. Its body is so sturdy that it can survive even if the atmosphere is poisonous, the temperature is freezing or hellish, or the gravity is strong or weak. So although all your neural patterns are contained inside the mainframe computer, you have all the sensations coming from the avatar. For all intents and purposes, you are inhabiting it. The advantage of this approach is that there is no need for messy, expensive booster rockets or space stations. You never face the problem of weightlessness, asteroid collisions, radiation, accidents, etc. And at the speed of light, you have taken the fastest possible journey to the stars. From your point of view, this trip is instantaneous. All you remember is entering the laboratory and then instantly arriving at your destination. I call this laser porting, and it is perhaps the most convenient and rapid way to reach the stars. A Type 1 civilization a century from now may be able to conduct the first laser porting experiments, but for Type 2 and 3, laser porting may be the preferred method of transportation across the galaxy because they will most likely have already colonized distant planets with self-replicating robots. Perhaps a Type 3 civilization will have a vast laser porting superhighway connecting the stars in the Milky Way, with trillions of souls in transit at any one time. Although this idea seems to provide the most convenient way to explore the galaxy, to actually create the laser port requires solving several practical problems. Placing your connectome on a laser beam is not a problem, since lasers can in principle transport unlimited amounts of information. The main problem is to create a network of relay stations along the way that receive your connectome, amplify it, and send it along to the next station. As we mentioned, the Oort cloud extends several light years from a star, so the Oort cloud from different stars can overlap. Those stationary comets in the Oort cloud may provide ideal sites for these relay stations. As we have seen, these relay stations can only be set up at slower than light speed velocities. One way to solve this problem is to use a system of laser sails, which travel at a significant fraction of the speed of light. Once these laser sails land on the Oort cloud comet, they could use nanotechnology to make copies of themselves and assemble a relay station using the raw materials found on the comet. So although the original relay stations will have to be made at sub-light speeds, after that our connectomes could be free to roam at light speed. Laser porting could be used not only for scientific purposes but also for recreation. We might take a vacation amongst the stars. We will first map out a sequence of planets, moons or comets we wish to visit. No matter how hostile or dangerous the environment may be, we might make a checklist of the types of avatars that we wish to inhabit. So on each planet there is an avatar waiting for us with all the traits and superpowers we desire. When we reach that planet, we assume the identity of that avatar, travel across the planet and enjoy all the incredible sights. Afterwards, we return the robot for the next customer to use. Then we laser port to the next destination. In a single vacation, we may be able to explore several moons, comets and exoplanets. We never have to worry about accidents or illnesses, since it is just our connectome roaming across the galaxy. So when we gaze into the heavens at night, wondering if anyone is out there, although it may appear to be cold, still and empty, perhaps the night sky is teeming with trillions of travelers being sent at the speed of light across the heavens. This, however, leaves open the second possibility, that faster than light travel might be possible for a Type 3 civilization. A new law of physics enters into this picture. This is the realm of the Planck energy, that scale at which bizarre new phenomena occur that violate the usual laws of gravity. To understand why the Planck energy is so important, it is essential to realize that at present all known physical phenomena from the Big Bang to the motion of subatomic particles can be explained by two theories: Einstein's general theory of relativity and the quantum theory. Together they represent the bedrock physical laws governing all matter and energy. The first, general relativity, is the theory of the very big. Relativity explains the Big Bang, the properties of black holes and the evolution of the expanding universe. The second is the theory of the very small. The quantum theory describes the properties and motion of atomic and subatomic particles that make possible all the electronic miracles in our living room. The problem is that these two theories cannot be united into a single comprehensive one. They are quite dissimilar, based on different assumptions, different mathematics, and different physical pictures. If a unified field theory were possible, the energy at which unification will take place is the Planck energy. This is the point at which Einstein's theory of gravity breaks down completely. It is the energy of the Big Bang and the energy at the center of a black hole. The Planck energy is 10 to the 19 billion electron volts, which is a quadrillion times the energy produced by a Large Hadron Collider at CERN, the most powerful particle accelerator on the Earth. At first it will seem hopeless to prove the Planck energy, since it is so enormous, but a Type 3 civilization which has more than 10 to the 20 times more than energy than a Type 1 civilization has enough power to do so, so a Type 3 civilization may be able to play with the fabric of space-time and bend it at will. They may reach this incredible energy scale by creating a particle accelerator much bigger than the Large Hadron Collider. The LHC is a circular tube in the shape of a donut, 17 miles in circumference, surrounded by huge magnetic fields. When a stream of protons is injected into the LHC, the magnetic field bends their path into a circle. Then pulses of energy are periodically sent into the donut, causing them to accelerate. There are two beams of protons traveling inside the tube in opposite directions. When they reach a maximum velocity, they collide head-on, unleashing the energy of 14 trillion electron volts, the largest burst of energy ever created artificially. The LHC has made many headlines, including the discovery of the elusive Higgs boson, which won the Nobel Prize for two physicists, Peter Higgs and François Engelbert. One of the main purposes of the LHC was to complete the last piece of the puzzle, called the Standard Model of Particles, which is the most advanced version of the quantum theory and gives us a complete description of the universe at low energies. The Standard Model is sometimes called the theory of almost everything, because it accurately describes the low energy universe that we see around us, but it cannot be the final theory for several reasons. It makes no mention of gravity. Worse, when we combine the Standard Model and Einstein's theory of gravity, the hybrid theory blows up, giving us nonsense, with calculations that become infinite. It has a strange collection of particles that seem quite contrived. It has 36 quarks and antiquarks and a series of Young-Mills gluons and leptons and Higgs bosons. It has 19 or so free parameters that have yet to be put in by hand. These masses and couplings are not determined by the theory. No one knows why they have these numerical values. It's hard to believe that the Standard Model, with its motley collection of subatomic particles, is nature's final theory. It's like taking a Scotch tape and wrapping up a platypus, aardvark, and a whale and calling it Mother Nature's finest creation, then product of millions of years of evolution. The next big particle accelerator currently in the planning stage is the International Linear Collider, consisting of a straight tube approximately 30 miles long, in which beams of electrons and anti-electrons will collide. The current plan is that it will be based on the Kitakami Mountains of Japan and is expected to cost roughly 20 billion, of which half will be supplied by the Japanese government. Although the maximum energy of the ILSC will be only 1 trillion electron volts, in many ways it will be superior to the LHC. When smashing protons into each other, the collision is extremely difficult to analyze because the proton has a complicated structure. It contains 3 quarks held together by particles called gluons. The electron, however, has no known structure. It looks like a point particle. Therefore, when an electron collides with an anti-electron, it is a clean, simple interaction. Even with these advances in physics, our Type 0 civilization cannot directly prove the Planck energy, but this is within the realm of a Type 3 civilization. Building accelerators like the ILSC may be a crucial step in being able to one day test how stable space-time is and determine whether we might be able to take shortcuts through it. Eventually, an advanced civilization might build a particle accelerator the size of the asteroid belt. A circular beam of protons will be sent around the belt, guided by gigantic magnets. On Earth, particles are sent inside a large circular tube containing a vacuum, but since the vacuum of outer space is better than any vacuum on the Earth, this accelerator does not need a tube at all. All it needs is a series of gigantic magnetic stations placed strategically around the belt, making a circular path for the proton beam. It is somewhat like a relay race. Each time the protons go past a station, a surge of electrical energy powers the magnets, which should kick the proton beam so that it moves to the next station at the correct angle. Each time the proton beam passes by a magnetic station, more energy is pumped into the beam in the form of laser power, until it gradually reaches the Planck energy. Once the accelerator attains this energy, it can focus that energy onto a single point. A wormhole should open up there. It will then be injected with enough negative energy to stabilize it so it doesn't collapse. What might trip through the wormhole look like? No one knows, but an educated guess was made by the physicist Kip Thorne of Caltech when he helped to advise the directors of the film Interstellar. Thorne used a computer program to trace the paths of light beams as they went past one, so that you could get a visual effect for what this trip might look like. Unlike the usual cinematic representations, this was the most rigorous attempt yet to visualize the journey on film. In addition to building a gigantic particle accelerators, there are a few other ways that physicists have considered exploiting wormholes. One possibility is that the Big Bang was so explosive that it might have inflated tiny wormholes that existed in the infant universe 13.8 billion years ago. When the universe began to expand exponentially, these wormholes may have expanded with it. This means that although at present no one has ever seen one, they might be a natural occurring phenomenon. Some physicists have speculated about how to go about finding one. Another possibility, also explored by Kip Thorne and his collaborators, is to find a tiny one in the vacuum and then expand it. Our latest understanding of space is that it may be frothing with tiny wormholes as universes spring into existence and then vanish again. So if you had enough energy, you might be able to manipulate a pre-existing wormhole and inflate it. There is one problem, however, with all these proposals. The wormhole is surrounded by particles of gravity called gravitons. As you are able to pass through it, you will encounter quantum corrections in the form of gravitational radiation. Normally, quantum corrections are small and can be ignored, but calculations show that these corrections are infinite as you pass through a wormhole, so the radiation will likely be lethal. Also, the radiation levels are so strong that the wormhole may close, making a passage impossible. There is a debate among physicists today about how dangerous it might be to travel through a wormhole. Einstein's relativity is no longer of any use as we enter the wormhole. Quantum effects are so large that we need a higher theory to take us through. Currently, the only one capable of doing this is string theory, which is one of the strangest ever proposed in physics. What theory can unify general relativity and the quantum theory at the Planck energy? Einstein spent the last 30 years of his life chasing after a theory of everything that could allow him to read the mind of God, but he failed. This remains one of the biggest questions facing modern physics. The solution will reveal some of the most important secrets of the universe, and using it we may be able to explore time, travel, wormholes, higher dimensions, parallel universes, and even what happened before the Big Bang. Furthermore, the answer will determine whether or not humanity can travel the universe at faster than light velocities. To understand this, we have to understand the basis of the quantum theory, the Heisenberg uncertainty principle. This innocent-sounding principle states that no matter how sensitive your instruments, you can never know both the velocity and position of any subatomic particle, like an electron. There is always a quantum fuzziness. Thus a startling picture emerges. An electron is actually a collection of different states, with each state describing an electron in a different position with a different velocity. But quantum theory states otherwise. When you look in a mirror, you are not seeing yourself as you really are. You are made up of a vast collection of waves, so the image you see in the mirror is actually an average, a composite of all of them. There is even a small probability that some of these waves can spread out all over your room and into space. In fact, some of your waves can even spread out to Mars or beyond. These waves are called quantum corrections or quantum fluctuations. Normally these corrections are small, so the common sense notion is perfectly fine, since we are a collection of atoms and can only see averages, but at the subatomic level these quantum corrections can be large, so that electrons can be several places at the same time and exist in parallel states. Fortunately, physicists can calculate these quantum corrections for subatomic particles and make predictions for them, some of which are valid to incredible accuracy, to 1 part in 10 trillion. In fact, the quantum theory is so accurate that it is perhaps the most successful theory of all time. Nothing else can match its accuracy when applied to ordinary matter. It may be the most bizarre theory ever proposed in history. But it has one small thing going for it. It is undeniably correct. So the Heisenberg uncertainty principle forces us to reevaluate what we know about reality. One result is that black holes cannot really be black. Quantum theory says that there must be quantum correction to pure blackness, so black holes are actually gray. Many textbooks say that at the center of a black hole or at the beginning of time, there is a singularity, a point of infinite gravity, but infinite gravity violates the uncertainty principle. Similarly, it is often stated that a pure vacuum is a state of pure nothingness. The concept of zero violates the uncertainty principle, so there is no such thing as pure nothingness. And there is no such thing as absolute zero, the temperature at which all motion stops. When we try to formulate a quantum theory of gravity, a problem occurs, however. The quantum corrections of Einstein's theory are described by particles we call gravitons. Just like a photon is a particle of light, a graviton is a particle of gravity. Gravitons are so elusive that they have never been seen in the laboratory, but physicists are confident that they do exist, since they are essential to any quantum theory of gravity. When we try to calculate with these gravitons, however, we find that quantum corrections are infinite. Quantum gravity is riddled with corrections that blow up the equations. Some of the greatest minds in physics have tried to solve this problem, but all have failed. So this is one goal of modern physics, to create a quantum theory of gravity where the quantum corrections are finite and calculable. In other words, Einstein's theory of gravity allows for the formation of wormholes, which may be one day giving us shortcuts throughout the galaxy, but his theory cannot tell us if these wormholes are stable or not. To calculate these quantum corrections, we need a theory that combines relativity with a quantum theory. So far, the leading and only candidate to solve this problem is something called the string theory, which says that all matter and energy in the universe is composed of tiny strings. Each vibration of the string corresponds to a different subatomic particle, so the electron is not really a point particle. If you had a super microscope, you could see that it is not a particle at all but a vibrating string. The electron appears to be a point particle only because the string is so tiny. If the string vibrates at a different frequency, it corresponds to a different particle, such as a quark, mu, meson, neutrino, photon, and so on. That is why physicists have discovered such a ridiculous number of subatomic particles. There are literally hundreds, all because they are just different vibrations of a tiny string. In this way, string theory can explain the quantum theory of subatomic particles. According to the string theory, as the string moves, it forces time-space to curl up exactly as Einstein predicted, and hence it unifies Einstein's theory and the quantum theory in a very pleasing fashion. This means that subatomic particles are just like musical notes. The universe is a symphony of strings. Physics represents the harmonies of these notes, and the mind of God that Einstein chased after for so many decades is cosmic music resonating through hyperspace. So how does string theory banish the quantum corrections that have bewildered the physicists for decades? String theory possesses something called supersymmetry. For every particle there is a partner, a superparticle or sparticle. For example, the partner of the electron is the selectron, the partner of the quark is the s-quark. So we have two types of quantum corrections, those coming from ordinary particles and those from the s-particles. The beauty of string theory is that the quantum corrections coming from these two sets of particles exactly cancel each other out. Thus, string theory gives us a simple but elegant way to eliminate these infinite quantum corrections. They vanish because the theory reveals a new symmetry that gives the theory its mathematical power and beauty. To artists, beauty may be an ethereal quantity that they aspire to capture in their worlds, but to a theoretical physicist, beauty is symmetry. It is also an absolute necessity when probing the ultimate nature of space and time. For example, if I have a snowflake and rotate it by 60 degrees, the snowflake remains the same. In the same way, a kaleidoscope creates beautiful patterns because it uses mirrors to repeatedly duplicate an image so it feels 360 degrees. We say that the snowflake and kaleidoscope both possess radial symmetry, that is, they remain the same after a certain radial rotation. Let's say I have an equation containing many subatomic particles and then I shuffle or rearrange them amongst each other. If the equation remains the same after interchanging these particles, I will then say that the equation has a symmetry. Symmetry is not just a matter of aesthetics, it is a powerful way to eliminate imperfections and anomalies in your equations. If you rotate the snowflake, you can rapidly spot any defects by comparing the rotated version with the original. If they are not the same, then you have a problem that needs correcting. In the same way, when constructing a quantum equation, we often find that a theory is infested with tiny anomalies and divergences, but if the equation has a symmetry, then these defects are eliminated. In the same way, supersymmetry takes care of the infinites and imperfections often found in a quantum theory. As a bonus, it turns out that supersymmetry is the largest symmetry ever found in physics. Supersymmetry can take all known subatomic particles and mix them together or rearrange them while preserving the original equation. In fact, supersymmetry is so powerful that it can take Einstein's theory, including the graviton and the subatomic particles of the standard model, and rotate them or interchange them. This gives us a pleasing and natural way to unify Einstein's theory of gravity and subatomic particles. String theory is like a gigantic cosmic snowflake, except that each prong of the snowflake represents the entire set of Einstein equations and the standard model of subatomic particles. So each prong of the snowflake represents all the particles of the universe. As we rotate the snowflake, all the particles of the universe are interchanged. Some physicists have noted that even if Einstein had never been born and billions of dollars were never spent on smashing atoms to create a standard model, then all of 20th century physics might have been discovered if you simply possessed string theory. Most importantly, supersymmetry cancels the quantum corrections of particles with those of sparticles, leaving us with a finite theory of gravity. That is the miracle of string theory. This also explains the answer to the question most often heard about string theory: why does it exist in 10 dimensions and why not 13 or 20? This is because the number of particles in string theory can vary with the dimensionality of space and time. In higher dimensions we have more particles, since there are more ways in which particles can vibrate. When we try to cancel the quantum corrections from the particles against the corrections from the sparticles, we find that this cancellation can only happen in 10 dimensions. Usually mathematicians create new imaginative structures that physicists later incorporate into their theories. For example, the theory of curved surfaces was worked out by mathematicians in the 19th century and was later incorporated into Einstein's theory of gravity in 1915. But this time the reverse happened. String theory has opened up so many new branches of mathematics that the mathematicians were startled. Young aspiring mathematicians who usually scorn applications of their discipline have to learn string theory if they want to be on the cutting edge. Although Einstein's theory allows us for the possibility of wormholes and faster than light travel, you need a string theory to calculate how stable these wormholes are in the presence of quantum corrections. In summary, these quantum corrections are infinite, so removing these infinities is one of the fundamental problems in physics. String theory eliminates these quantum corrections because it has two types of quantum corrections that precisely cancel each other. This precise cancellation between particles and sparticles is due to supersymmetry. However, as elegant and powerful as string theory is, it is not enough. It must ultimately face the final challenge, which is experiment. Although this picture is compelling and persuasive, there are valid criticisms one can make of the theory. First, since the energy at which string theory unifies all of physics is the Planck energy, no machine on Earth is powerful enough to rigorously test it. A direct test would involve creating a baby universe in the laboratory, which is obviously out of the question given current technology. Second, like any physical theory, it has more than one solution. For example, Maxwell's equation, which governs light, have an infinite number of solutions. This is not a problem because at the very beginning of any experiment we specify what we are studying, whether it's a light bulb, laser or a TV. Then later, given these initial conditions, we solve the equations of Maxwell. But if we have a theory of the universe, then what are these initial conditions? Physicists believe that a theory of everything should dictate its own initial state. That is, they would prefer that the initial conditions of the Big Bang somehow emerge from the theory itself. String theory, however, does not tell you which of its many solutions is the correct one for our universe, and without initial conditions, string theory contains an infinite number of parallel universes called the multiverse, each one as valid as the next. So we have an embarrassment of riches with string theory, predicting not only our own familiar universe but perhaps an infinite number of other equally valid alien universes as well. Third, perhaps the most startling prediction of string theory is that the universe is not 4-dimensional at all but exists in 10 dimensions. In all of physics, nowhere have we seen a prediction this bizarre, a theory of space-time that selects out its own dimensionality. This was so strange that many physicists at first dismissed it as science fiction. We know that any object in our universe can be described by three numbers: length, width, and height. If we add time, then four dimensions can describe any event in the universe. For example, if I want to meet someone in New York City, I might say that we should meet at 42nd Street and 5th Avenue on the 10th floor at noon, but to a mathematician the need for only 3 or 4 coordinates might seem arbitrary, since there is nothing special about 3 or 4 dimensions. Why should the most fundamental feature of the physical universe be described by such ordinary numbers? So mathematicians have no problem with the string theory, but to visualize this number of dimensions, physicists often use analogies. When I was a child, I used to spend many hours gazing at a Japanese tea garden in San Francisco, watching the fish swim in the shallow pond. I asked myself a question that only a child would ask: what would it be like to be a fish? What a strange world they would see. I thought that they would think that the universe was only two-dimensional. They could only swim in this limited space by moving sideways, but never up or down. Any fish who dare mention a third dimension beyond the pond would be considered a crackpot. I then imagined there was a fish living in the pond who would scoff anyone that mentioned hyperspace, since the universe was just what you could touch and feel. The more I imagined this, the more strange it seemed to me. Similarly, perhaps we are this fish. If string theory is proven correct, it means that there are unseen dimensions beyond our familiar four-dimensional world. But where are these higher dimensions? One possibility is that 6 of the 10 original dimensions have curled up, so they cannot be seen anymore. Think of taking a sheet of paper and rolling it up in a tight tube. The original sheet was two-dimensional, but the rolling up process has created a one-dimensional tube. From a distance you only see the one-dimensional tube, but in reality it is still two-dimensional. In the same way, string theory says that the universe was originally 10-dimensional, but for some reason 6 of these dimensions curled up, leaving us with the illusion that our world has only 4. Although this feature of string theory seems fantastic, efforts are underway to actually measure these higher dimensions. But how do higher dimensions help string theory unify relativity and quantum mechanics? If you try to unify the gravitational, nuclear, and electromagnetic forces into a single theory, you find that there is not enough room in 4 dimensions to do this. They are like pieces of a jigsaw puzzle that don't fit together, but once you start to add more and more dimensions, you find enough room to assemble these lower theories, like matching jigsaw pieces together to make the whole. For example, think of a two-dimensional world of flatlanders who, like Cookie Men, can only move left or right, but never up. Imagine that there was once a beautiful three-dimensional crystal that exploded, showering fragments out of flatland. Over the years, the flatlanders have reassembled this crystal into 2 large fragments, but as hard as they try, they are unable to fit these last 2 fragments together. Then one day a flatlander makes the outrageous proposal that if they move one fragment up into the unseen third dimension, then the 2 fragments will fit together and form a beautiful 3-dimensional crystal. So the key to recreating the crystal was moved. Even though string theory fits the data neatly, we still need to test it. Although, as discussed, a direct test is not possible. Most physics is done indirectly. For example, we know that the sun is made mainly of hydrogen and helium, yet no one has ever visited the sun. We know the sun's composition because we analyze it indirectly, looking at sunlight through a prism which breaks it up into bands of colors. By studying these bands within the rainbow, we can identify the fingerprint of hydrogen and helium. In the same way, string theory might be proven by a variety of indirect tests. Since each vibration of the string corresponds to a particle, we can, in our particle accelerator, search for entirely new particles that represent higher octaves of the string. The hope is that by smashing protons together at trillions of volts, you briefly create a new particle among the debris that is predicted by string theory. This in turn may help explain one of the great unsolved mysteries in astronomy. In the 1960s, when astronomers examined the rotation of the Milky Way galaxy, they found something strange. It was rotating so fast that by Newton's laws it should fly apart, yet the galaxy has been stable for about 10 billion years. In fact, the galaxy rotated about 10 times faster than it should be according to traditional Newtonian mechanics. This posed a tremendous problem. Either Newton's equations were wrong, or there was an invisible halo of unknown matter surrounding the galaxies, increasing their mass sufficiently for gravity to hold them together. This meant that perhaps the pictures we see of gorgeous galaxies with their beautiful spiral arms are incomplete, that they are actually surrounded by a gigantic invisible halo that is 10 times more massive than the visible galaxy. Since photographs of galaxies only show the beautiful swirling mass of stars, whatever is holding the mass together must not interact with light. It must be invisible. Astrophysicists dubbed this missing mass as dark matter. Its existence forced them to revise their theories, which said that the universe is made mainly of atoms. We now have maps of dark matter throughout the universe. Although it is invisible, it bends starlight just as anything with mass would. Therefore, by analyzing the distortion of starlight surrounding galaxies, we can use computers to calculate the presence of dark matter and map its distribution across the universe. Sure enough, this map shows that most of the total mass of a galaxy exists in this form. In addition to being invisible, dark matter has gravity, but you can hold it in your hand since it does not interact with atoms at all. It will pass through your hand, the floor, and through the crust of the Earth. It will oscillate between New York and Australia as if the Earth did not exist at all, except that it will be bound by Earth's gravity. So although dark matter is invisible, it still interacts via gravity with other particles. One theory is that dark matter is a higher vibration of the superstring. The leading candidate is the superpartner of the photon, which is called the photino. It has all the right properties to be dark matter. It is invisible because it does not interact with light, and yet it has a weight and is stable. There are several ways to prove this conjecture. The first is to create dark matter directly with the Large Hadron Collider by smashing protons into each other. For a brief instant of time, a particle of dark matter will be formed inside the accelerator. If this is possible, it will have enormous repercussions for science. It will represent the first time in history that a new form of matter has been found that is not based on atoms. If the LHC is not powerful enough to produce dark matter, then perhaps the ILC can. There is also another way to prove this conjecture. The Earth is moving in a wind of this invisible dark matter. The hope is that a dark matter particle may smash into a proton inside a particle accelerator, creating a shower of subatomic particles that might be photographed. At present, there are physicists around the world patiently waiting to find the signature of a collision between matter and dark matter in their detectors. There is a Nobel Prize waiting for the first physicist to do so. If dark matter is found, either with particle accelerators or with ground-based sensors, we will be able to compare its properties with those predicted by string theory. In this way, we will have evidence to evaluate the validity of the theory. Although finding dark matter will be a great step towards proving string theory, other proofs are possible. For example, Newton's law of gravity governs the motion of large objects like stars and planets, but little is known about the force of gravity acting over small distances, like a few inches or feet. Since string theory postulates higher dimensions, this means that Newton's famous inverse square law should be violated at small distances because Newton's laws is predicted on 3 dimensions. Another possible avenue is to send gravity wave detectors into space. The Laser Interferometer Gravitational Wave Observatory, based in Louisiana and Washington State, was successful in picking up gravity waves from colliding black holes in 2016 and colliding neutron stars in 2017. A modified version of the space-based Laser Interferometer Space Antenna may be able to detect gravity waves from the instant of the Big Bang. The hope is that one might be able to run the videotape backward and make conjectures about the nature of the pre-Big Bang era. This would allow a crude test of some of the predictions of string theory concerning the pre-Big Bang universe. Still, other tests of string theory may involve finding other exotic particles predicted by the theory, such as micro-black holes which resemble subatomic particles. We have seen how physics allows us to speculate about civilizations far into the future, making reasonable conjectures based on their energy assumptions. Civilizations can be expected to evolve from a Type 1 planetary civilization to the Type 2 stellar and finally a Type 3 galactic. A galactic civilization in turn is likely to explore the galaxy via von Neumann probes or by laser torping their consciousness across the galaxy. The key point is that a Type 3 civilization may be able to access the Planck energy. The point where space-time becomes unstable and faster than light travel might be possible. But to calculate the physics of faster than light travel, we need a theory that goes beyond Einstein's theory, which might well be the string theory. The hope is that using string theory we'll be able to calculate the quantum corrections necessary to analyze exotic phenomena such as time travel, interdimensional travel, wormholes, and what happened before the Big Bang. String theory should be capable of calculating how much gravitational radiation you would encounter when you pass through the wormhole and answer all of our questions. Another hotly debated question among physicists is what happens if you enter a wormhole and go backwards in time. If you then kill your grandfather before you are born, then you have a paradox. How can you exist at all if you just kill your ancestor? Einstein's theory actually allows for time travel, but says nothing about how to resolve these paradoxes. String theory, because it is a finite theory in which everything can be calculated, should be able to resolve all these mind-twisting paradoxes. At present, however, because of the complexity of the mathematics of string theory, physicists have not been able to apply it to these questions. This is a mathematical problem, not an experimental one, so perhaps one day an enterprising physicist will be able to definitely calculate the properties of wormholes and hyperspace. Instead of idly speculating about faster than light travel, a physicist using string theory has the ability to determine whether this might be possible, but we will have to wait until the theory is sufficiently understood to make this determination. So there is a possibility that a Type 3 civilization may be able to use a quantum theory of gravity to achieve faster than light travel spaceships, but what would this imply? The question remains, what happens when a Type 3 civilization masters the Planck energy and begins to make contact with these branches of humanity? History may repeat itself. For example, the Great Diaspora ended with the coming of the airplane and modern technology, giving us a rapid international transportation network. Today we can take a short plane trip over continents that once took our ancestors tens of thousands of years to cross. In the same way, when we make the transition from a Type 2 to a Type 3, we will by definition have enough power to explore the Planck energy, at which point space-time becomes unstable. If we assume that this makes faster than light travel possible, it means that a Type 3 civilization might be able to unify the various Type 2 colonies that are spread out across the galaxy. Given our common human heritage, it may make possible the creation of a new galactic civilization as envisioned by Asimov. As we have seen earlier, the amount of genetic divergence that humanity may experience over several tens of thousands of years in the future is roughly the same as the divergence that has already occurred since the Great Diaspora. The key point is that we have maintained our humanity throughout. This also means that Type 3 archaeologists curious about ancient human migrations may try to retrace the ancient migration routes of various branches of Type 2 civilizations across the galaxy. Galactic archaeologists may look for signs of various ancient Type 2 civilizations. In the Foundation saga, our heroes are in search of the ancestral planet that gave birth to the Galactic Empire, whose name and location were lost in the chaos of galactic prehistory. Given that the human population numbers in the trillions, with millions of inhabited planets, this seems like a hopeless task, but by exploring the most ancient planets in the galaxy, they find ruins of the earliest planetary colonies. They see how planets were abandoned because of war, disease, and other calamities. Likewise, a Type 3 civilization may emerge from a Type 2 and try to retrace the various branches that were explored centuries earlier by sublight-speed spaceships, in the same way that our current civilization is enriched by the presence of so many different types of cultures, each with a different history and perspective. However, eventually any advanced civilization will have to face the ultimate challenge of their existence, which is the end of the universe itself. We have to ask the question, can an advanced civilization, with all its vast technology, evade the death of everything there is? Perhaps the only hope for the intelligent life is to evolve into a Type 4 civilization.